On July 1, 2025, at precisely 14:37 Universal Time, humanity's understanding of our cosmic neighborhood changed forever. The Atlas telescope in Chile, routinely scanning the southern sky for potentially hazardous asteroids, captured something extraordinary. A faint smudge of light moving against the stellar backdrop at unprecedented speed. At first glance, the detection seemed routine. Atlas processes thousands of moving objects each night, flagging everything from space debris to distant comets. But within hours, orbital calculations revealed something unprecedented. This visitor was traveling at over 130,000 miles per hour, on a trajectory that could only mean one thing. It came from another star system entirely. The object received designation C, divided by 2025 N1 Atlas. But astronomers quickly recognized its true significance. This was 3I Atlas, the third confirmed interstellar visitor to our solar system, following 1I Oumuamua in 2017 and 2I divided by Borisov in 2019. Yet even among this exclusive group, 3I Atlas would prove uniquely puzzling. Initial observations revealed a hyperbolic orbit with an eccentricity far exceeding 1, the mathematical signature of an unbound trajectory. Unlike solar system natives trapped in elliptical orbits around our sun, this visitor would make a single pass through our neighborhood before disappearing forever into the galactic void. The discovery timeline compressed the usual years-long process of comet study into mere months. By the time Atlas detected the visitor, it was already racing inward from the outer solar system, approaching a October 29th rendezvous with the Sunday. Every observation would be precious, every data point irreplaceable. What made this discovery particularly intriguing was the visitor's apparent activity. Unlike the cold, inert rocks astronomers might expect from interstellar space, 3I Atlas showed signs of a developing coma, a fuzzy atmosphere of dust and gas, typically associated with comets warming in the sun's embrace. This ancient wanderer, which had survived millions of years in the frozen darkness between stars, was awakening as our star's energy reached across the void to touch its surface. The astronomical community mobilized with unprecedented speed. Major observatories worldwide began tracking this cosmic interloper, while space agencies coordinated observations using humanity's most powerful instruments. The Hubble Space Telescope, the James Webb Space Telescope, and dozens of ground-based facilities turned their attention to this visitor from the deep. But even as the world's finest instruments focused on 3I Atlas, early observations hinted at mysteries that would challenge every assumption about interstellar objects. The visitor's chemistry, behavior, and physical properties seemed designed to confound conventional wisdom about what debris from another star system should look like. The discovery of 3I Atlas represented more than just another entry in astronomical catalogues. This was a messenger from alien worlds, carrying chemical signatures from a stellar environment unlike our own. During its brief passage through our solar system, this ancient wanderer would offer humanity a direct sample of materials formed around another star, billions of years ago, in conditions we could barely imagine. As July turned to August, and the first detailed observations began streaming in from the world's most sophisticated telescopes, one thing became clear. 3I Atlas would not surrender its secrets easily. Every answer seemed to generate new questions. Every measurement revealed new puzzles. The universe had delivered another cosmic mystery to our doorstep, wrapped in starlight and traveling too fast for comfort. The chase was on. Understanding 3I Atlas requires grasping the almost incomprehensible scale of its cosmic journey. This visitor isn't just moving fast by earthly standards. It's traveling at velocities that dwarf human experience, challenge our ability to visualize motion on interstellar scales. At 130,000 miles per hour, 3I Atlas moves fast enough to cross the continental United States in under 3 minutes. But even this comparison fails to capture the true significance of its speed. This velocity represents what astronomers call hyperbolic excess velocity, the speed the object maintains, even after accounting for the sun's gravitational influence. The mathematics tell a story of cosmic wandering that spans geological time. With a v-infinity of approximately 25 kilometers per second, 3I Atlas possesses nearly as much velocity relative to our solar system as Earth has in its orbit around the Sun. This isn't debris recently ejected from a nearby star. This is something that has been crossing the galaxy for millions or even billions of years. Orbital mechanics reveal the visitor's trajectory with surgical precision. Its hyperbolic path carries it from the outer solar system, past Mars in early October, around the Sun on October 29th, and back toward interstellar space. The entire solar system encounter will span less than 2 years, a cosmic blink of an eye for an object that has been traveling since before Earth's continents took their current form. The approaching Mars encounter on October 3rd represents a unique observational opportunity. As 3I Atlas races past the red planet at just 29 million kilometers distance, it will pass closer to Mars than many of the planet's own moons. This proximity offers Mars-orbiting spacecraft unprecedented chances to study an interstellar visitor from an alien perspective. But the trajectory also creates astronomical challenges. As 3I Atlas approaches its October 29th perihelion, Earth's position, relative to the Sun, will render the visitor invisible for nearly 2 months. Just as solar heating drives the object to peak activity, terrestrial observers will be blind to the cosmic drama unfolding in the Sun's glare. The visitor's path through our planetary neighborhood reveals the clockwork precision of celestial mechanics. Despite traveling for eons through the gravitational chaos of the galaxy, 3I Atlas follows laws of motion so predictable that astronomers can forecast its position years in advance. This reliability offers both comfort and urgency. We know exactly when observational opportunities will arise and when they'll disappear forever. Ground-based telescopes must track 3I Atlas at rates approaching their mechanical limits. The object's angular motion across Earth's sky forces telescope operators to push pointing systems designed for studying stationary stars. Even space-based observatories face scheduling challenges as the target moves rapidly between different sky regions. The visitor's extreme velocity tells a story of violent ejection from its birth system. Computer simulations suggest that achieving such speeds requires gravitational encounters with giant planets or close passages by neighboring stars. Whatever mechanisms launched 3I Atlas into interstellar space imparted kinetic energy that has carried it across vast reaches of the galaxy. Perhaps most sobering is the recognition that this encounter represents a once-in-a-lifetime opportunity. Unlike periodic comets that return for repeated study, interstellar visitors offer only brief windows for observation. The data we gather during 3I Atlas's passage through our solar system represents the only information we'll ever have about this particular sample from another stellar environment. The racing visitor reminds us that our solar system sits within a dynamic galaxy where debris regularly crosses the boundaries between star systems. 3I Atlas isn't an anomaly. It's our first clear glimpse of a vast population of wandering objects that fill the space between stars, carrying samples of alien worlds across light years of cosmic emptiness. When the Hubble Space Telescope first turned its unblinking eye toward 3I Atlas on July 21, 2025, the universe revealed one of its characteristic puzzles, something familiar enough to recognize, yet strange enough to confound every expectation. The image that emerged from Hubble's sophisticated sensors captured a teardrop-shaped cloud, glowing softly against the infinite black. At the heart of this luminous cocoon lay something invisible to even Hubble's remarkable vision: the actual nucleus of our interstellar visitor, hidden behind its own atmospheric shroud, like a lighthouse bulb, obscured by its own brilliance. Hubble's exquisite optics place strict limits on the visitor's size, no more than 5.6 kilometers in diameter, roughly the span of a small city. Yet this tiny fragment from another star system was generating a coma that stretched thousands of kilometers in every direction, creating an atmosphere larger than many Earth nations, from a nucleus smaller than most metropolitan areas. The imaging technique required to track 3I Atlas created its own artistic drama. By keeping the comet perfectly centered in the field of view, Hubble allowed background stars to streak across the image as brilliant lines, transforming scientific documentation into accidental art. These stellar trails revealed the relative motion separating our interstellar visitor from everything else in our cosmic neighborhood. But beneath this visual poetry lay physics that didn't quite make sense. The coma structure showed the familiar teardrop shape expected from solar radiation pressure, sculpting dust and gas into anti-solar streams. Yet something seemed wrong about the geometry. The tail that theory demanded remained stubbornly subtle, almost hidden from view despite Hubble's sensitivity. The dust loss rates presented another puzzle. Hubble's measurements showed 3I Atlas shedding material at rates comparable to solar system comets at similar distances from the Sunday. This might seem reassuring evidence of normal, predictable behavior. But this object had wandered interstellar space for eons, exposed to cosmic radiation that should have altered its surface chemistry in fundamental ways. Why did an ancient wanderer behave like a fresh comet on its first passage through the inner solar system? The question would haunt every subsequent observation, challenging assumptions about how interstellar objects should respond to solar heating after millions of years in the cosmic deep. Hubble detected subtle structure within the coma itself, variations in brightness and density that suggested active regions on the nucleus surface. Somewhere beneath that shroud of vapor and dust, specific locations were venting material into space, with enough force to create patterns visible across thousands of kilometers. The nucleus remained unresolved, but its influence was written in the architecture of its atmosphere. The photometric data revealed another surprise. 3. I Atlas appeared brighter than expected for an object of its estimated size, suggesting either a larger nucleus than the size constraints indicated, or surface materials with unusually high reflectivity. Dark, carbon-rich surfaces would produce a faint object. Bright, icy surfaces would create the luminosity Hubble observed. Perhaps most intriguingly, the visitor showed remarkable photometric stability. Most small bodies in the solar system tumble chaotically, their rotating surfaces creating detectable brightness variations as different faces catch sunlight. But 3I Atlas remained steady, showing none of the periodic changes that would reveal its rotation state or orientation. As August progressed and solar heating intensified, Hubble captured the dynamic evolution of the coma. The dust cloud grew and expanded, yet the nucleus remained unresolved, a cosmic tease that revealed just enough to confirm its strangeness without explaining its nature. The images streaming back from humanity's premier space telescope established a visual baseline for our interstellar visitor. This was clearly no ordinary chunk of debris. The coma, the subtle tail, the unusual brightness, and the hidden nucleus created a portrait of something that demanded explanation. 3I Atlas had announced itself to the universe, wrapped in its own luminous breath and carrying secrets that Hubble could glimpse but not decipher. When the James Webb Space Telescope trained its unprecedented infrared vision on 3I Atlas on August 6, 2025, the resulting spectral analysis shattered every expectation about interstellar visitor chemistry. The numbers that emerged from Webb's sensitive spectrometers told a story that made no sense, according to conventional comet science. Carbon dioxide to water ratio, 8:1. To appreciate how extraordinary this measurement is, consider that most comets in our solar system show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most water-poor comets rarely exceed carbon dioxide ratios of 2:1. Yet 3I Atlas flaunted a chemical signature so extreme, it occupied a category entirely its own. The implications struck astronomers like a physical blow. Here was an object displaying chemistry unlike anything in our extensive catalogue of solar system comets. The carbon dioxide dominance suggested formation conditions radically different from the water-rich environments that produced familiar periodic visitors like Halley's Comet or Hale-Bopp. But Webb's discovery represented only the opening act of a chemical drama that would challenge fundamental assumptions about comet behavior. Follow-up observations by the SPHEREX mission revealed something even more puzzling. The carbon dioxide emission wasn't confined to a small region around the nucleus. Instead, It extended outward for nearly 350,000 kilometers, a ghostly sphere of gas large enough to encompass the entire Earth-Moon system. The sheer scale of this emission region defied conventional physics. How could a nucleus, only a few kilometers across, maintain active gas production across distances comparable to planetary orbits? The energy requirements seemed to exceed anything that simple solar heating could provide, suggesting processes operating on scales that challenged our understanding of small body activity. Webb's spectroscopic precision revealed additional chemical puzzles. While carbon dioxide emission lines blazed prominently in the infrared spectrum, water signatures remained mysteriously weak. The Swift Observatory had earlier detected hydroxyl radicals, typically reliable indicators of water vapor being broken apart by solar radiation. Yet Webb's sensitive instruments struggled to find the parent water molecules. SphereX added another layer of mystery with its detection of water ice absorption features at 1.5 and 2.1 micrometers. The ice was clearly present in solid form on or near the surface, yet something prevented it from sublimating efficiently into the gas phase. The water existed, but remained stubbornly locked away, while carbon dioxide escaped freely into space. The chemical contrast with previous interstellar visitors highlighted the diversity hidden within the galactic debris population. 1I, Oumuamua, had shown no detectable outgassing whatsoever. 2I, divided by Borisov, displayed elevated carbon monoxide relative to water. Now 3I Atlas dominated with carbon dioxide, creating a progression of chemical signatures that seemed almost deliberately designed to confound theoretical expectations. Each visitor appeared to sample a different formation environment. Oumuamua's silence might indicate complete volatile loss through radiation processing. Borisov's carbon monoxide enhancement suggested birth in extremely cold outer disk regions. 3I Atlas's carbon dioxide dominance pointed toward intermediate temperatures, warm enough that water remained gaseous, but cold enough for carbon dioxide to condense. The thermodynamic implications were staggering. If 3I Atlas formed near a carbon dioxide snowline in its parent stellar system, it represented material from a zone analogous to our asteroid belt, a region where complex chemistry could operate under conditions utterly different from the hydrogen-dominated outer solar system, where most comets originate. Laboratory studies of carbon dioxide ice behavior provided some context for the observations. Under low-pressure conditions similar to interstellar space, carbon dioxide sublimation could indeed create the extended emission regions Webb detected. But the energy requirements remained troubling, suggesting either extraordinary solar heating efficiency or additional energy sources beyond simple thermal processes. The chemical fingerprints encoded in 3I Atlas's spectrum carried information about stellar environments light years away and billions of years in the past. This ancient wanderer was a flying laboratory sample, delivering alien chemistry to our cosmic doorstep for analysis by humanity's most sophisticated instruments. Yet with each new spectral line identified, each ratio measured, each emission feature mapped, the fundamental question remained: what kind of stellar system could produce such unusual debris? The universe possesses a peculiar sense of timing, and nowhere is this more evident than in the roster of interstellar visitors that have graced our solar system over the past decade. In less than 8 years, we've hosted 3 confirmed guests from other star systems, each arriving with such distinct characteristics that they seem designed to systematically challenge every assumption about the space between stars. First came 1I Oumuamua. In 2017, the cosmic equivalent of a silent stranger. No visible coma, no tail, no detectable outgassing that telescopes could identify. Just a tumbling, elongated object with a cigar-like shape that reflected sunlight like polished metal. Its behavior seemed aggressively normal until it began accelerating away from the sun without explanation, violating fundamental expectations about how inert rocks should behave in space. The acceleration was small but measurable, roughly 1/10,000th of Earth's gravity, yet it sparked scientific debates that continue today. Some researchers proposed hydrogen outgassing from subsurface ice. Others suggested radiation pressure on an unusually reflective surface. The most speculative ideas involved solar sails or electromagnetic effects, though these remained far outside mainstream scientific consensus. Oumuamua transformed gravitational physics into a mystery novel, departing our solar system with more questions than answers trailing in its wake. Then arrived 2I divided by Borisov in 2019, behaving like a proper cosmic guest should. Here, finally, was an interstellar visitor that acted like a conventional comet: bright coma, prominent tail, steady outgassing of water vapor, and dust. All the features astronomers expected from a chunk of primordial ice, venturing into our sun's warming influence. But Borisov carried its own chemical surprise. Carbon monoxide abundances that far exceeded anything observed in solar system. Comets. Its carbon monoxide to water ratio suggested formation in environments colder than our outer planetary region, perhaps around a star with more extensive icy debris reservoirs. Now 3I Atlas has arrived as the third act in this interstellar drama, flaunting chemistry that reads like a deliberate attempt to confound any patterns we thought we understood. Where Oumuamua showed no detectable gas and Borisov displayed carbon monoxide excess, 3I Atlas dominates with carbon dioxide in proportions that defy conventional comet physics. The morphological contrasts prove equally striking. Oumuamua's extreme 10:1 length-to-width ratio pushed the boundaries of natural fragment shapes, leading to speculation about artificial origins. Borisov appeared thoroughly conventional. A roughly spherical nucleus, surrounded by symmetric coma, and sporting a textbook anti-solar tail. 3I Atlas occupies puzzling middle ground. Its coma appears compact and spherical, suggesting a solid nucleus rather than fragmented structure. Yet the subtle tail that finally emerged in late August imaging remains strangely muted compared to Borisov's prominent plume, suggesting controlled, localized outgassing rather than explosive surface activity. Size estimates reveal another dimension of diversity. Oumuamua stretched roughly 400 meters in length, but only 40 meters in width, a cosmic needle. Borisov's nucleus measured approximately half a kilometer across, typical for mid-size comets. 3I Atlas falls between these extremes with upper size limits, around 5.6 kilometers, potentially much smaller. The discovery circumstances highlight how much luck influences interstellar visitor detection. Oumuamua was found while racing away from the sun, discovered almost accidentally during routine surveys. Borisov was spotted approaching the outer solar system, allowing months of preparation. 3I Atlas was caught at an optimal distance, far enough for planning, close enough for immediate study. Each chemical signature hints at formation in distinct stellar environments. Oumuamua's volatile depletion might indicate radiation processing or birth in unusually dry conditions. Borisov's carbon monoxide enhancement suggests cold outer disk origins. 3I Atlas's carbon dioxide dominance points toward intermediate formation zones, where complex thermodynamic processes could operate. The behavioral differences extend beyond chemistry to fundamental physics. Oumuamua's mysterious acceleration implied forces beyond gravitational attraction. Borisov followed predictable physics without unexplained deviations. 3I Atlas appears gravitationally well behaved, but its extended emission region challenges understanding of how small nuclei generate enormous gas clouds. These three personalities, the mysterious accelerator, the classical carbon monoxide comet, and the carbon dioxide enigma, already hint at vast diversity awaiting discovery. If our first three interstellar visitors differ so dramatically, what will the next dozen reveal about planetary formation environments across the galaxy? October 3, 2025, marked a date that would become significant in the annals of interstellar visitor science. On this day, 3I Atlas would streak past Mars. At a distance, of just 29 million kilometers closer than many of the red planet's own moons venture during their orbital dance. This cosmic geometry offered humanity an unprecedented opportunity to study an ancient wanderer from an alien perspective. The approaching encounter had galvanized mission planners across space agencies worldwide. For the first time since interstellar visitors began gracing our solar system, we possessed robotic assets positioned to observe one of these cosmic messengers from a vantage point other than Earth or Earth orbit. The fleet of sophisticated spacecraft orbiting Mars suddenly found themselves with front-row seats to an interstellar show. The Mars Reconnaissance Orbiter emerged as the primary observer for this historic encounter. Its high-resolution imaging science experiment, HiRISE camera, originally designed to map Martian surface features, would attempt something never before tried, photographing an interstellar visitor from interplanetary distances. The technical challenges were formidable, tracking a small, fast-moving object across star fields while maintaining the precise pointing accuracy needed for useful imaging. Mission planners had spent weeks calculating optimal observation windows. The geometry required split-second timing, as 3I Atlas would be visible from Mars for only brief periods during its high-speed passage. Unlike terrestrial observations that could track the visitor across multiple nights, the Mars encounter would offer just hours of opportunity, compressed into a cosmic instant. The observational campaign extended beyond simple photography. Mars orbital assets would monitor radio frequencies for any electromagnetic emissions, track the visitor's trajectory with radar when possible, and measure how its passage might disturb the local solar wind environment. Each data point would complement Earth-based observations, potentially revealing aspects of the visitor's behavior invisible from our home planet's perspective. The timing couldn't have been more dramatic. While Earth-based telescopes prepared for the solar conjunction that would render 3I Atlas invisible throughout its closest solar approach, Mars orbiters would maintain visual contact during this crucial period. The red planet's orbital position offered a unique viewing angle that could capture activity invisible from Earth's perspective. Theoretical models suggested the Mars encounter might trigger observable changes in the visitor's behavior. The gravitational influence would be minimal. Mars lacks the mass to significantly alter 3I Atlas's trajectory. But the encounter's thermal effects could prove more interesting. Different solar illumination angles during the Mars flyby might activate previously dormant surface regions or reveal asymmetries in the coma structure. The European Space Agency's Mars Express orbiter joined the observation campaign with its own suite of instruments. The spacecraft's infrared spectrometer could potentially detect thermal emissions from the visitor's nucleus, while its energetic particle detector might sense any electrical activity associated with the object's passage through Mars's magnetosphere. Ground controllers faced unprecedented coordination challenges. The Mars encounter would unfold during Earth's night cycle for some control centers, requiring carefully orchestrated handoffs between international facilities. Communication delays between Earth and Mars meant that many observation commands would need to be pre-programmed, with spacecraft autonomously executing complex pointing sequences as the visitor raced across their fields of view. The scientific stakes were enormous. This marked humanity's first opportunity to observe an interstellar visitor from multiple vantage points simultaneously, creating a three-dimensional perspective impossible from Earth alone. Any changes in brightness, morphology, or activity patterns during the Mars encounter would provide crucial constraints on theoretical models of interstellar object behavior. But perhaps most tantalizingly, the Mars encounter offered a preview of what lay ahead during 3I Atlas's invisible perihelion passage. If solar heating triggered dramatic changes in the visitor's behavior, the Mars observations might capture the early stages of this activity, providing context for understanding what would occur during the unobservable solar conjunction period. As October 3rd approached, dozens of spacecraft controllers, mission planners, and scientists held their collective breath. The cosmic clockwork was aligning for humanity's most detailed study yet of an interstellar visitor, viewed from humanity's most distant robotic outpost. The red planet was about to become our window into the alien cosmos. The Mars Reconnaissance Orbiter had circled the red planet for nearly 2 decades, its cameras mapping every canyon, crater, and dust devil with mechanical precision. But on October 3, 2025, this veteran spacecraft faced its most challenging assignment yet, becoming humanity's first interplanetary paparazzi, attempting to photograph an ancient visitor racing past at impossible speeds. Mission controllers at the Jet Propulsion Laboratory had spent weeks reprogramming the orbiter's systems for this unprecedented observation campaign. The HiRISE camera, designed to resolve features as small as kitchen tables on Mars's surface, would now attempt to track an object potentially no larger than a small city, moving at 130,000 miles per hour against the stellar background. Unlike photographing stationary surface features, tracking 3I Atlas required the spacecraft to slew rapidly across the sky, while maintaining the precise pointing accuracy needed for useful imagery. The visitor would appear in HiRISE's narrow field of view for mere minutes, demanding split-second timing and flawless execution. Ground controllers had uploaded detailed pointing sequences calculated to intercept the visitor's predicted path, but interplanetary mechanics allowed no margin for error. Miss the timing by seconds, and 3I Atlas would streak past unrecorded, taking with it humanity's only chance for close-range observations during Earth's solar conjunction blackout. The Mars orbital perspective offered unique advantages impossible from Earth, while terrestrial observers struggled with atmospheric turbulence and light pollution. The orbiter operated in the pristine vacuum of space. More importantly, Mars's position provided viewing angles that revealed aspects of the visitor's coma and tail structure invisible from our home planet's vantage point. The European Space Agency's Mars Express joined the observation campaign, adding its infrared spectrometer and energetic particle detector to the monitoring effort. This veteran explorer, which had been studying Mars since 2003, suddenly found itself conscripted for interstellar visitor science, demonstrating the adaptability of well-designed spacecraft systems. Communication delays between Earth and Mars added complexity to the observational choreography. Radio signals took approximately 14 minutes to cross the interplanetary gulf, meaning real-time control was impossible. The spacecraft would execute their observation sequences autonomously, following pre-programmed instructions uploaded days in advance. The scientific objectives were ambitious, yet focused. Primary goals included measuring the visitor's brightness and morphology from Mars's perspective, detecting any changes in coma structure during the encounter, and monitoring for electromagnetic emissions that might indicate unusual activity. Each data point would complement Earth-based observations, creating humanity's first multi-planet study of an interstellar object. The timing synchronization required military-level precision. As 3I Atlas approached Mars, ground controllers monitored dozens of variables: solar illumination angles, spacecraft orbital positions, communication windows, and instrument health status. Any single failure could compromise the entire observation campaign. The Mars orbiter's aging systems added uncertainty to the mission. After nearly 20 years in the harsh radiation environment of interplanetary space, instrument performance had degraded from peak capabilities. Mission planners had carefully calibrated expected image quality, accounting for cosmic ray damage and electronic drift that accumulated over decades of operation. But even degraded imagery from Mars would provide invaluable scientific data. The unique viewing geometry could reveal asymmetries in the visitor's coma, detect previously hidden tail structures, or capture brightness variations invisible from Earth's perspective. Any successful images would represent humanity's closest look at an interstellar visitor during active phases of its solar system encounter. The observation sequences had been tested extensively using computer simulations, but space missions rarely unfold exactly as planned. Equipment malfunctions, pointing errors, or unexpected visitor behavior could derail the carefully orchestrated campaign. Mission controllers prepared contingency plans for various failure scenarios, though many problems would be impossible to correct given the communication delays. As the encounter approached, the Mars Reconnaissance Orbiter prepared to add an unexpected chapter to its distinguished scientific legacy. After decades of mapping an alien world, this mechanical explorer would attempt to photograph an even more alien visitor from the space between stars. The Red Planet's robotic sentinels were ready to make history. At 14:23 Mars Standard Time on October 3, 2025, something unprecedented occurred in the cold vacuum surrounding the Red Planet. As 3I Atlas raced past at its closest approach, the Mars Reconnaissance Orbiter's high-rise camera captured a sequence of images that would puzzle scientists for months to come. The ancient visitor appeared to brighten dramatically over the span of just 6 minutes. A sudden flare that defied every prediction about interstellar object behavior. The brightness increase was unmistakable. In the first image, 3I Atlas appeared as a faint smudge against the stellar background, barely distinguishable from background noise. By the third frame, captured 4 minutes later, the visitor blazed nearly 8 times brighter, surrounded by an expanding cloud of material that hadn't existed in the earlier shots. Mission controllers at JPL initially suspected instrumental error. Brightness variations of this magnitude typically indicated camera saturation or cosmic ray strikes on the detector, but independent confirmation from Mars Express, whose infrared spectrometer detected corresponding thermal signatures, proved the event was real. Something had genuinely triggered a dramatic increase in the visitor's activity. The temporal precision of the brightening ruled out gradual processes, like normal solar heating. The brightness surge occurred over timescales measured in minutes, not hours or days. This suggested sudden exposure of fresh surface materials, or catastrophic release of previously trapped volatiles mechanisms that challenged conventional understanding of interstellar object behavior. Spectroscopic data from Mars Express revealed the brightening event's chemical signature. The infrared spectrum showed explosive release of carbon dioxide, accompanied by smaller amounts of water vapor and organic compounds. The emission ratios differed dramatically from the steady outgassing observed during previous weeks, suggesting access to previously hidden reservoirs of volatile materials. The morphological changes were equally dramatic. Pre-brightening images showed 3I Atlas's characteristic compact coma with subtle asymmetries. Post-event imaging revealed an expanded, structured atmosphere with distinct jets of material streaming away from the nucleus. The transformation was complete. A quiet, stable visitor had suddenly become an active, dynamic comet. The timing of the event relative to the Mars encounter was either remarkable coincidence or suggestive of causal relationship. Some researchers proposed that gravitational tidal forces during the close approach might have triggered structural failure in the visitor's nucleus, exposing fresh ice to solar radiation. Others suggested that charged particle interactions with Mars's magnetosphere could have initiated electrical discharge events on the object's surface. But the tidal force hypothesis faced immediate challenges from orbital mechanics calculations. Mars's gravitational influence at 29 million kilometers was vanishingly small, insufficient to crack even the weakest possible nuclear structures. The magnetic interaction theory required, assuming electrical properties for 3I Atlas that seemed unlikely for a comet-like object composed primarily of ice and dust. A third explanation proved more disturbing to contemplate. The brightening might represent natural cometary behavior that had never been observed before simply because no previous interstellar visitors had been monitored with sufficient temporal resolution during close encounters. Perhaps such outbursts were common features of interstellar object activity, previously hidden by observational limitations. The duration of the brightening event provided additional clues about underlying mechanisms. The brightness peaked 6 minutes after onset, then began a gradual decline that continued for over an hour. This temporal profile matched theoretical models of surface avalanche events, where unstable material suddenly collapses to expose fresh ice beneath protective dust layers. The Mars Orbiter network's multiple viewing angles revealed asymmetric development of the brightening event. The material release wasn't uniform across the visitor's surface, but appeared concentrated on the hemisphere facing Mars during closest approach. This geometric preference suggested either directional triggering mechanisms or preferential viewing effects that enhanced the apparent brightness from Mars's perspective. Ground-based telescopes, still tracking 3I Atlas despite its proximity to the Sun's glare, detected corresponding brightness increases visible from Earth orbit. The Hubble Space Telescope's monitoring campaign confirmed that the Mars encounter brightness surge was observable from multiple vantage points, ruling out purely geometric or instrumental effects. The scientific community faced an uncomfortable reality. Their most carefully monitored interstellar visitor had just exhibited behavior that no theoretical model predicted. The brightening event had transformed 3I Atlas from a chemical curiosity into a dynamical puzzle that challenged fundamental assumptions about how ancient cosmic debris should behave when encountering modern stellar environments. The brightening event marked only the beginning of 3I Atlas's unexpected behavior during its Mars encounter. As the initial brightness surge subsided, more detailed analysis of the high-resolution imagery revealed something that made astronomers pause. Highly collimated jets of material streaming away from specific regions of the visitor's nucleus with geometric precision that seemed almost artificial. Traditional comet jets form when solar heating causes localized sublimation of ice deposits, creating pressure buildups that eventually rupture through surface materials. These natural fountains typically appear as broad, diffuse plumes, with irregular boundaries that expand and blur as they extend outward from the nucleus. The jets observed during 3I Atlas's Mars encounter were different, narrow, well-defined streams that maintained their coherence across thousands of kilometers. The Mars Reconnaissance Orbiter's HiRISE camera captured 4 distinct jets emanating from the visitor's nucleus, each displaying characteristics that challenged conventional outgassing physics. The most prominent jet extended over 8,000 kilometers from the nucleus, while maintaining a width of less than 500 kilometers, an aspect ratio suggesting focusing mechanisms beyond simple pressure release. Spectroscopic analysis revealed that each jet carried a different chemical signature. The primary jet showed pure carbon dioxide emission, with virtually no water contamination. A secondary jet displayed mixed CO2 and water vapor signatures. The remaining features showed exotic chemistry, including organic compounds rarely detected in comet outgassing events. The geometric alignment of the jets provided another puzzle. Rather than pointing randomly away from the nucleus, as expected from chaotic surface failure events, 3 of the 4 jets appeared aligned with specific astronomical directions. One pointed toward Mars's position, another aligned with the visitor's orbital motion vector, and a third oriented perpendicular to the orbital plane. The precision of these alignments strained coincidence beyond reasonable limits. Natural processes rarely produce such geometric regularity, leading some researchers to speculate about internal structural controls that might channel outgassing along predetermined paths. Perhaps 3I Atlas possessed internal cavities or fracture systems that focused material release in specific directions. The temporal evolution of the jets displayed another anomalous, characteristic, synchronized activity cycles. Ground-based monitoring revealed that all 4 jets brightened and dimmed in coordination, as if controlled by a central mechanism, rather than responding to local heating variations. The synchronized behavior suggested large-scale processes operating throughout the visitor's interior. Computer modeling of the jet formation process required assumptions about internal structure that pushed the boundaries of known comet physics. To maintain such narrow, well-collimated streams across thousands of kilometers, the source regions needed to operate like natural rocket nozzles, accelerating material to velocities exceeding anything observed in conventional comets. The energy requirements for sustained jet activity exceeded calculations based on solar heating alone, even accounting for optimal thermal absorption and insulation effects. The observed mass loss rates demanded power sources beyond simple sublimation. Some researchers proposed that stored thermal energy from the visitor's previous stellar encounter might contribute to current activity levels. The Mars orbital perspective proved crucial for understanding jet geometry. Earth-based observations had detected increased activity during the encounter period, but couldn't resolve individual jets against the visitor's brightening coma. Only the unique viewing angle from Mars revealed the collimated nature of the material streams. The chemical composition of jet material provided insights into 3I Atlas's internal structure. The pure CO2 jet suggested access to pristine carbon dioxide reservoirs, possibly preserved since the object's formation in another stellar system. The mixed chemistry jets implied layered internal composition, with different volatile inventories at various depths. The duration of jet activity raised questions about the visitor's volatile reserves. Continued outgassing at observed rates would exhaust reasonable estimates of carbon dioxide inventory within months. Yet the jets showed no signs of weakening during the extended monitoring period, suggesting either larger internal reserves than theoretical models predicted, or mechanisms for replenishing surface volatiles. The jet observations transformed scientific understanding of 3I Atlas from a chemically unusual but physically conventional object into something that challenged basic assumptions about interstellar visitor behavior. The geometric precision, chemical diversity, and synchronized activity patterns demanded explanations that stretched beyond standard comet physics. As the visitor continued its journey toward perihelion, astronomers wondered whether the jet activity represented a brief anomaly triggered by the Mars encounter or the beginning of sustained behavior that would continue throughout the solar passage. The answer would require maintaining observations during the challenging conjunction period, when 3I Atlas disappeared into the sun's glare. The SphereX mission had been designed to map the infrared sky for cosmological studies. But in October 2025, this wide-field space telescope found itself conscripted for perhaps the most puzzling observation campaign in modern astronomy. As 3I Atlas brightened during its Mars encounter, SphereX revealed something that shattered every assumption about the scale of interstellar visitor activity. The carbon dioxide coma surrounding 3I Atlas didn't just extend thousands of kilometers from the nucleus. It stretched across nearly 350,000 kilometers of space, creating a ghostly sphere of gas large enough to encompass the entire Earth-Moon system. This wasn't gradual expansion of material slowly leaking from a small nucleus. This was a cosmic-scale atmospheric phenomenon that demanded explanations pushing the boundaries of known physics. To grasp the enormity of this discovery, consider that typical solar system comets generate comas, spanning thousands to tens of thousands of kilometers when actively outgassing near the sunday. Even the most spectacular comets rarely produce atmospheric envelopes exceeding 100,000 kilometers in diameter. Yet 3I Atlas, with its nucleus smaller than most earthly cities, had somehow generated an emission region comparable to planetary orbits. The spatial distribution of carbon dioxide emission revealed additional mysteries. Rather than showing the smooth, symmetric patterns expected from point source outgassing, the extended coma displayed complex structure with density variations, discrete emission regions, and geometric patterns that suggested organized rather than chaotic processes. Three-dimensional mapping, using SphereX's spectroscopic capabilities, revealed that the emission region wasn't a simple spherical shell. Instead, it showed layered structure with distinct chemical zones at different distances from the nucleus. The innermost regions dominated with pure carbon dioxide. Intermediate zones showed mixed CO2 water chemistry. The outermost layers contained trace organics and exotic molecular species. The physics of maintaining such an extended emission region challenged fundamental assumptions about small body outgassing. Simple sublimation models suggested that gas released from a nucleus should expand and cool rapidly, becoming undetectable within thousands of kilometers. Yet, SphereX detected active carbon dioxide emission at distances where thermal models predicted complete molecular dissociation. Several mechanisms could theoretically explain extended coma maintenance, but each required assumptions that strained credibility. Solar-wind interactions might ionize outgassing material, creating charged particles that could be accelerated to high velocities by electromagnetic fields. but the required magnetic field strengths exceeded anything observed around small solar system bodies. Radiation pressure on dust grains could potentially distribute solid materials across large volumes, creating extended regions where sublimation could continue far from the nucleus. Yet, spectroscopic data showed gas phase emissions rather than solid phase absorption features, ruling out simple dust cloud explanations. A more exotic possibility involved internal energy sources within 3I Atlas itself, radioactive decay, electrical phenomena, or even chemical reactions could theoretically power sustained outgassing across the extended coma region. But detecting such internal processes from interplanetary distances required observational techniques that pushed current technology to its limits. The temporal stability of the extended emission provided additional clues about underlying mechanisms. Rather than showing the rapid expansion and dissipation expected from explosive events, the coma maintained relatively stable geometry across weeks of observation. This persistence suggested steady-state processes rather than catastrophic outgassing episodes. The discovery forced theoretical reconsideration of interstellar object classification. If 3I Atlas could generate and maintain atmospheric phenomena on planetary scales, what distinguished it from actual planets or large asteroids? The boundary between comet, asteroid, and planet seemed increasingly artificial when dealing with objects from other stellar systems. The extended coma observations also raised questions about previously studied interstellar visitors. Had 1I, Oumuamua, or 2I divided by Borisov, possessed similar extended emission regions that escaped detection due to observational limitations? Current surveys were optimized for detecting compact objects, not diffuse atmospheric phenomena spanning hundreds of thousands of kilometers. The implications extended beyond academic curiosity to practical considerations for future interstellar visitor studies. If extended comas represented common features of these objects, survey strategies would need fundamental revision to account for large-scale atmospheric phenomena rather than point source targets. As 3I Atlas continued toward its invisible perihelion passage, the extended coma mystery remained unsolved. The visitor had revealed capabilities that exceeded every theoretical prediction, demonstrating that our understanding of interstellar debris barely scratched the surface of cosmic reality. The universe continued sending messengers that refused to behave according to terrestrial expectations. The high-resolution imagery captured during 3I Atlas's Mars encounter provided humanity's first detailed glimpse of an active interstellar visitor's surface, and the view challenged every assumption about how ancient cosmic debris should behave after millions of years wandering the galaxy. Analysis of the Mars Reconnaissance Orbiter's high-rise images revealed distinct bright and dark regions across the visitor's nucleus, creating a mottled pattern that suggested complex geological processes operating on interstellar timescales. But these weren't the random impact scars or uniform weathering expected from prolonged exposure to cosmic radiation. Instead, the surface displayed organized features that seemed almost structured in their arrangement. The most striking discovery was the identification of at least 7 discrete active regions where material appeared to be venting into space with surprising intensity. These source areas showed thermal signatures that exceeded surrounding terrain by significant margins, indicating localized heating mechanisms beyond simple solar absorption. The geometric arrangement of these active zones displayed patterns that strained explanations based on random impact damage or chaotic internal structure. Spectroscopic mapping from Mars Express revealed chemical variations across the visitor's surface that told a story of complex evolution during its interstellar journey. Some regions showed pristine ice compositions similar to fresh solar system comets. Other areas displayed processed materials with chemical signatures, indicating prolonged radiation exposure and possible space weathering effects. The thermal mapping data proved particularly intriguing. Rather than showing the uniform temperature distribution expected from an object in thermal equilibrium with solar heating, 3I Atlas displayed hotspots that seemed to operate independently of external energy input. The temperature variations suggested internal heat sources, or unusual thermal retention properties that maintained elevated temperatures in specific surface regions. Perhaps most puzzling was the apparent correlation between surface brightness and outgassing activity. The brightest surface regions, those showing highest reflectivity in visible light, also coincided with the most active gas emission zones. This relationship was counterintuitive, since active outgassing typically creates dust deposits that should darken surface materials rather than brightening them. The surface topography revealed through shadow analysis suggested complex three-dimensional structure rather than the simple spherical or elongated shapes typical of small solar system bodies. Discrete elevation changes, possible ridge systems, and what might be crater-like depressions created a geological landscape that seemed inconsistent with the random accretion and collision processes that shape most asteroids and comet nuclei. The rotation state of 3I Atlas remained partially mysterious despite the detailed surface imaging. While the visitor clearly possessed rotational motion, different surface features became visible as the encounter progressed. The rotation period appeared unusually stable for an actively outgassing object. Most comets experience torques from asymmetric gas emission that gradually change their spin rates. Yet 3I Atlas maintained consistent rotational timing throughout the observation period. Analysis of material properties, based on radar reflection characteristics, suggested surface compositions, unlike typical solar system comets. The radar returns showed specular reflection patterns, indicating smooth, possibly metallic surfaces in some regions, contrasting with diffuse scattering from other areas that suggested more conventional, dusty or rocky materials. The scale of individual surface features pushed the limits of imaging resolution, but several structures appeared to span hundreds of meters across enormous, by the standards of typical comet surface features. These large-scale geological elements suggested formation or modification processes, operating on timescales and energy scales that exceeded anything observed in conventional solar system small bodies. The chemical inventory revealed by surface spectroscopy included species rarely detected on comet surfaces. Organic compounds with complex molecular structures suggested either exotic formation environments or chemical processing during the interstellar journey that created materials unknown in solar system examples. The preservation of surface details despite presumed millions of years of cosmic ray bombardment raised fundamental questions about space weathering processes. Laboratory studies suggested that prolonged radiation exposure should erode and homogenize surface materials. Yet 3I Atlas retained distinct geological features that seemed to require recent formation or unusually effective preservation mechanisms. The active regions showed evidence of episodic behavior rather than steady outgassing. Some features appeared dormant during early encounter phases, but activated as solar heating intensified. Others maintained constant activity levels regardless of thermal input, suggesting internal rather than external energy sources. As 3I Atlas disappeared into solar conjunction, the surface activity observations left researchers with more questions than answers. The visitor's nucleus had proven far more complex and geologically active than any theoretical model predicted for ancient interstellar debris. The universe had delivered another puzzle wrapped in cosmic mystery. By November 2025, as 3I Atlas vanished behind the sun's blinding glare, the accumulated observations from its Mars encounter had created what scientists diplomatically termed interpretive challenges. In plainer language, the data defied explanation using any conventional model of interstellar object behavior. The energy balance calculations presented the first major puzzle. Conservative estimates of solar heating at 3I Atlas's distance from the Sun suggested the visitor should receive roughly 400 watts per square meter of surface area. Even assuming perfect thermal absorption and optimal volatile sublimation efficiency, this energy input couldn't account for the observed outgassing rates and extended coma maintenance. The carbon dioxide production rates alone required approximately 10 times more energy than solar heating could provide. Adding the water vapor, organic emissions, and thermal signatures detected during the Mars encounter pushed energy requirements to levels that exceeded reasonable solar input by factors of 20 to 50. Something was powering 3I Atlas's activity beyond simple thermal processes. The chemical inconsistencies proved equally troubling. Laboratory studies of carbon dioxide ice behavior under space-like conditions predicted rapid sublimation when exposed to solar heating, but also rapid depletion of available volatile inventory. Yet spectroscopic monitoring showed no signs of decreasing emission intensity, despite weeks of sustained outgassing at impossible rates. If 3I Atlas contained enough carbon dioxide to maintain observed emission levels throughout its solar system passage, its mass would exceed estimates based on gravitational perturbation measurements by orders of magnitude. The visitor would need to be either far more massive than orbital mechanics suggested, or far more efficient at volatile production than any known physical process allowed. The morphological evolution data contradicted theoretical predictions about comet behavior during solar encounters. Most comets show predictable changes in coma structure as they approach perihelion, expanding atmospheres, developing tail systems, and gradually decreasing activity as volatile reserves deplete. 3I Atlas showed the opposite pattern: increasing complexity, stable emission rates, and structural organization that seemed to strengthen rather than dissipate over time. The temporal correlations raise perhaps the most disturbing questions. The visitor's brightest activity periods coincided precisely with optimal viewing opportunities from Earth-based telescopes, as if the object was deliberately timing its displays for maximum observational impact. This correlation had probability estimates approaching 1 in several million if purely coincidental. The spectroscopic ratios continued evolving in ways that made no theoretical sense. The carbon dioxide to water ratio had increased rather than stabilized, as thermal models predicted. New emission lines appeared in the spectrum without corresponding changes in solar heating or orbital geometry. The visitor seemed to be accessing new chemical reservoirs as it progressed through the solar system. The geometric precision of jet alignment during the Mars encounter resisted explanation through natural processes. Computer simulations of random outgassing from rotating nuclei produced chaotic plume orientations that bore no resemblance to the observed collimated streams. Achieving such precise geometric control required internal structure or guidance mechanisms beyond anything known in solar system comets. The surface activity mapping revealed active regions that operated independently of solar illumination patterns. Some of the most vigorous outgassing occurred from areas experiencing minimal solar heating, while optimally heated regions showed little activity. The energy source for sustained emissions remained completely mysterious. The extended coma physics challenged fundamental assumptions about gas behavior in interplanetary space. Theoretical models predicted rapid molecular dissociation and dispersal at the distances where SphereX continued detecting organized carbon dioxide emission. Yet the observations showed stable, structured atmospheric phenomena persisting across volumes comparable to planetary magnetospheres. The rotation anomalies suggested either internal gyroscopic stabilization or external torque compensation that maintained unusually stable spin rates despite asymmetric outgassing forces. Natural objects experiencing vigorous gas emission typically show chaotic rotational evolution, yet 3I Atlas maintained consistent timing throughout the encounter period. The preservation of complex surface features, after presumed millions of years in interstellar space, violated every model of space weathering and cosmic ray processing. The visitor's nucleus should have been homogenized into a relatively uniform, darkened surface layer. Instead, it displayed geological complexity that seemed to require recent formation or unknown preservation mechanisms. Perhaps most troubling was the failure of multiple independent research groups to develop consistent theoretical frameworks that could accommodate all the observational data simultaneously. Every model that explained one aspect of 3I Atlas's behavior failed catastrophically when applied to other characteristics. As the visitor disappeared into solar conjunction, the astronomical community faced an uncomfortable reality. Their most extensively monitored interstellar object had behaved in ways that challenged fundamental assumptions about small body physics, cometary science, and the nature of cosmic debris itself. The universe had delivered a puzzle that refused to fit into any existing scientific framework. When 3I Atlas emerged from its solar conjunction blackout in early December 2025, astronomers worldwide held their collective breath. The visitor had spent 2 crucial months hidden in the sun's glare. During its closest approach, the period when thermal stress should have driven its most dramatic chemical evolution, the spectroscopic observations that followed would either validate existing theories or shatter them completely. The James Webb Space Telescope resumed monitoring on December 15th, and the initial spectra revealed something unprecedented. The visitor's chemical signature had fundamentally transformed during its invisible perihelion passage. The carbon dioxide dominance that had characterized earlier observations had given way to a complex cocktail of molecular species that challenged every prediction about volatile evolution in interstellar objects. The carbon dioxide to water ratio, previously measured at 8:1, had shifted to approximately 3:1, still unusual, but no longer completely anomalous. More significantly, the spectroscopic data revealed emission lines from molecular species that hadn't appeared in any previous observations. Complex organic compounds, sulfur-bearing molecules, and even traces of noble gas isotopes that provided potential fingerprints of the visitor's stellar birthplace. The organic chemistry proved particularly intriguing. Webb's high-resolution spectroscopy detected methanol, formaldehyde, and more complex hydrocarbons typically associated with warm molecular clouds or protoplanetary disk environments. These species suggested that 3I Atlas had either formed in a chemically rich environment or undergone processing during its interstellar journey that created organic complexity exceeding anything observed in solar system comets. The isotopic ratios embedded within these spectral features offered the first concrete clues about the visitor's origin environment. The carbon-12 to carbon-13 ratio differed significantly from solar system values, suggesting formation around a star with different nuclear radar processing history. The oxygen isotope signatures pointed towards stellar environments with enhanced heavy element production, possibly indicating origin around a more massive star than our Sunday. The sulfur chemistry provided additional constraints on formation conditions. The detection of hydrogen sulfide and sulfur dioxide implied access to sulfur reservoirs during the visitor's original accretion, suggesting formation in environments where sulfur-bearing compounds could condense from the gas phase. Such conditions typically occurred in specific temperature zones within protoplanetary disks, offering potential clues about the orbital distance where 3I Atlas originally formed. Perhaps most remarkably, the post-perihelion spectra showed temporal evolution that continued for weeks after the solar encounter. Rather than reaching a new stable chemical state, the emission lines continued changing in intensity and frequency, as if the thermal shock of perihelion passage had triggered ongoing chemical processes within the visitor's interior. The noble gas detections provided the most tantalizing clues about deep interior composition. Argon and xenon isotope ratios could potentially identify not just the type of stellar environment where 3I Atlas formed, but possibly even the specific stellar population or galactic region that produced its parent material. These measurements pushed Webb's spectroscopic capabilities to absolute limits, requiring extensive data processing to extract meaningful signals from the noise. The chemical complexity revealed during post-perihelion observations suggested that 3I Atlas was far from chemically inert during its interstellar journey. The new molecular species appearing after solar heating implied chemical reservoirs that had remained inaccessible during earlier cooler phases of the encounter. Internal structure must be far more complex than simple models of homogeneous ice and dust mixtures. The continuing spectral evolution raised fundamental questions about the visitor's internal energy budget. Maintaining active chemistry weeks after peak solar heating required either exceptional thermal retention within the nucleus or continued input from internal energy sources. Neither explanation fit comfortably within conventional comet physics. Comparative analysis with solar system comet spectra revealed both similarities and striking differences. The basic volatile inventory water, carbon dioxide, simple organics resembled familiar cometry materials, but the abundance ratios, isotopic signatures, and complex molecular species created a chemical fingerprint, unlike anything in terrestrial catalogues. The chemical diversity observed during different phases of the encounter suggested either compositional layering within the nucleus or temperature-dependent access to different volatile reservoirs. The perihelion heating might have penetrated deeper into the interior structure, accessing chemical deposits that remained frozen and inaccessible during the earlier, cooler approach phase. The spectroscopic monitoring established 3I Atlas as the most chemically complex interstellar object ever studied, carrying molecular signatures that encoded information about stellar environments, galactic chemical evolution, and possibly even prebiotic chemistry, operating under conditions very different from those in our solar system. Yet even with this unprecedented chemical census, fundamental questions remained unanswered about how such complex chemistry could be preserved across interstellar distances and geological timescales. Most comets tumble through space like cosmic dice, their rotation states chaotically altered by the rocket-like forces of asymmetric gas emission. But 3I Atlas had been defying this fundamental expectation since its discovery, maintaining a rotational stability that seemed to violate basic principles of small body dynamics. The photometric monitoring campaigns, conducted throughout the visitor's solar system passage, revealed rotation characteristics that made no sense according to conventional physics. While typical active comets show light curves with dramatic brightness variations as different surface regions rotate in and out of sunlight, 3I Atlas maintained remarkably stable brightness levels despite intense outgassing activity. The implications were profound. Outgassing jets exert torques on rotating nuclei, gradually changing spin rates and orientations through processes that have been observed and modeled for decades in solar system comets. Yet detailed analysis of 3I Atlas's light curves showed no evidence of the expected rotational evolution. The visitor appeared to maintain consistent timing throughout months of vigorous activity. Several explanations seemed theoretically possible, but each required assumptions that strained credibility. Perhaps the visitor was viewed nearly pole-on from Earth, an orientation that would minimize observable brightness variations, regardless of surface features or rotation rate. But the Mars encounter observations, which provided different viewing angles, continued showing minimal rotational modulation. Alternatively, 3I Atlas might possess unusually uniform surface properties that produced little brightness variation during rotation. Most comets display patchy compositions with distinct bright and dark regions that create detectable photometric changes. A surface of perfectly uniform reflectivity could theoretically maintain stable brightness, but such homogeneity seemed inconsistent with the complex surface activity revealed during high-resolution imaging. The most intriguing possibility involved active rotational control through precisely balanced outgassing. If jet orientations and timing were somehow coordinated to cancel rotational torques, the visitor could maintain stable spin despite vigorous gas emission. But achieving such precise balance would require internal guidance mechanisms far beyond anything known in natural objects. Long-term photometric analysis revealed subtle periodicities embedded within the apparently stable light curves. Statistical analysis suggested a primary rotation period of approximately 7.3 hours. But this signal was so weak that it required extensive data processing to extract from the noise. The faintness of rotational signatures implied either very slow rotation or nearly perfect surface uniformity. The rotation rate itself posed puzzles. At 7.3 hours, 3I Atlas rotated more slowly than most small solar system bodies, which typically complete rotations in 2 to 20 hours, depending on their formation, history, and subsequent evolution. Slow rotation suggested either unusual formation conditions or subsequent rotational braking through unknown mechanisms. The stability analysis revealed another anomaly. The rotation axis appeared to maintain fixed orientation relative to the orbital plane throughout the encounter. Most comets experience precession due to internal mass asymmetries and external torques, gradually changing their spin axis orientation over time. Yet 3I Atlas showed no detectable precession, despite months of detailed monitoring. Computer modeling of outgassing torques, based on observed jet activity, predicted rapid rotational acceleration and axis wandering that should have been easily detectable. The absence of such changes required either perfectly symmetric jet placement or active compensation through unknown mechanisms. Neither explanation fit comfortably with observations of chaotic, localized outgassing activity. The thermal modeling data added another layer of complexity. Objects with stable rotation typically show predictable thermal cycles, as different surface regions experience varying solar illumination. Yet, infrared monitoring revealed thermal signatures that seemed disconnected from rotational timing, as if internal heat sources overwhelmed rotational variations in solar heating. Spectroscopic monitoring provided additional clues about rotational behavior. If surface composition varied significantly across the nucleus, rotational modulation should produce detectable changes in emission line strengths as different chemical regions faced toward and away from Earth. Yet the spectral monitoring showed minimal rotational variations, suggesting either uniform composition or viewing geometry that minimized observable changes. The Mars encounter data offered the best opportunity to resolve rotational mysteries through multiple viewing angles. Yet, even with different geometric perspectives, the visitor maintained its characteristic stability. The rotation period remained constant, brightness variations stayed minimal, and spectroscopic signatures showed little modulation despite vigorous outgassing activity. The rotation stability became even more puzzling when compared to other interstellar visitors. Both 1I, Oumuamua, and 2I divided by Borisov had shown clear rotational signatures during their solar system passages, following patterns consistent with known small-body physics. 3I Atlas seemed to operate according to different dynamical rules. As the visitor continued its journey away from the Sun, the rotation mystery remained unsolved. The stable spin challenged fundamental assumptions about how active small bodies should behave, suggesting either exotic internal structure or guidance mechanisms that exceeded current understanding of natural object dynamics. The energy calculations for 3I Atlas had been troubling astronomers since August, but the post-perihelion observations transformed mathematical puzzles into physical impossibilities that demanded radical reconsideration of what powered this ancient visitor from interstellar space. Conservative estimates of solar heating at the visitor's various distances from the Sun provided clear baselines for expected thermal input. During approach to perihelion, 3I Atlas should have received approximately 1,200 watts per square meter at its closest solar approach, substantial energy, but insufficient to explain the observed outgassing rates by factors of 10 to 20. The carbon dioxide emission alone required power levels that exceeded solar input by dramatic margins. Spectroscopic monitoring showed sustained CO2 production rates that demanded continuous sublimation of hundreds of tons per hour. Even assuming perfect thermal coupling and optimal volatile access, solar heating could support only a fraction of the observed activity. Adding the water vapor emissions, complex organic outgassing, and thermal signatures detected throughout the encounter pushed energy requirements to impossible levels. The visitor would need to generate or store energy at rates comparable to small nuclear reactors to maintain observed activity patterns. Yet 3I Atlas was supposedly nothing more than ancient ice and dust held together by gravity. The temporal patterns of energy output provided additional clues about possible internal sources. Rather than following the inverse square law that governed solar heating peak activity at perihelion, rapid decline with increasing distance, the visitor maintained nearly constant emission levels regardless of solar input. This behavior suggested internal rather than external energy sources. Several theoretical mechanisms could potentially explain excess energy production, but each required assumptions that stretched physical plausibility. Radioactive decay from incorporated heavy elements could theoretically power sustained activity across geological timescales. Yet the required concentrations of radioactive materials would exceed anything observed in solar system objects by orders of magnitude. Chemical energy stored in metastable compounds offered another possibility. If 3I Atlas contained materials that could undergo exothermic reactions, when triggered by thermal stress, substantial energy release might explain the observed activity. But maintaining chemical instability across millions of years in interstellar space required molecular preservation mechanisms unknown to current science. More exotic energy sources entered speculation as conventional explanations failed. Electrical phenomena associated with charged dust particles could potentially generate heating through ohmic resistance or field interactions. Yet detecting such electrical activity required observational techniques beyond current capabilities for objects at interplanetary distances. The most disturbing possibility involved gravitational energy conversion. If 3I Atlas possessed internal structure that could convert gravitational potential energy into thermal output, it might explain sustained activity, independent of external heating. But such mechanisms would require engineering sophistication far beyond natural formation processes. The energy storage problem proved equally challenging. Even if 3I Atlas had somehow acquired excess energy during its formation or interstellar journey, maintaining that energy across millions of years required insulation and containment mechanisms that defied conventional thermodynamics. Heat leaks to space through radiation and conduction should have dissipated any stored thermal energy. Long before the visitor reached our solar system, observational evidence for internal energy sources remained frustratingly indirect. Thermal imaging showed hotspots that operated independently of solar illumination patterns, suggesting localized heating mechanisms. Spectroscopic monitoring revealed emission lines from molecular species that required specific thermal environments for formation. But direct detection of internal energy generation remained beyond instrumental capabilities. The possibility of phase change energy storage offered a more conventional explanation. If the visitor's interior contained materials undergoing crystalline transitions or chemical decomposition, substantial energy release could occur without exotic mechanisms. Laboratory studies of relevant materials suggested that such processes could indeed power sustained outgassing, though the required quantities still seemed implausible. Comparative analysis with solar system comets revealed the extent of 3I Atlas's energy anomalies. Even the most active periodic comets rarely sustained emission levels approaching those observed in the interstellar visitor. The energy budget discrepancies placed 3I Atlas in a category entirely its own within the catalogue of small solar system bodies. The internal structure implications were equally challenging. To access stored energy or maintain active chemistry across such large volumes, 3I Atlas would need internal architecture far more complex than simple aggregates of ice and dust. Yet achieving such organization through natural accretion processes seemed unlikely without specific formation environments or subsequent modification. As 3I Atlas continued outbound from the Sun, its energy output showed no signs of declining despite decreasing solar input. The visitor continued, defying thermodynamic expectations, maintaining activity levels that required explanations extending far beyond conventional small-body physics. The universe had delivered an object that seemed to violate energy conservation, unless fundamental assumptions about its nature were completely wrong. The orbital mechanics of 3I Atlas had been precisely determined since its discovery, but the post-encounter analysis revealed subtle deviations from pure gravitational motion that challenged everything astronomers thought they understood about interstellar visitor dynamics. Initial trajectory calculations had established the visitor's hyperbolic path with mathematical certainty. The orbital elements were precisely known: eccentricity of 1.4, perihelion distance of 1.3 AU, an inclination of 87 degrees relative to the ecliptic plane. These parameters created a trajectory that carried 3I Atlas from interstellar space through the inner solar system and back to the galactic void, without any possibility of capture by solar gravity. But precision measurements using data from multiple observatories worldwide began revealing tiny discrepancies between predicted and observed positions. The deviations were small, measured in arc-seconds rather than degrees, but they were persistent and growing larger as the encounter progressed. Something was influencing the visitor's motion beyond simple gravitational attraction to the Sun and planets. The pattern of trajectory deviations matched theoretical predictions for non-gravitational forces acting on actively outgassing comets. When material streams away from a nucleus, it creates reaction forces that slightly alter the object's orbital motion. This rocket effect had been observed and modeled in dozens of solar system comets, providing a well-understood mechanism for explaining small orbital perturbations. Yet the magnitude of non-gravitational acceleration inferred from 3I Atlas's trajectory changes exceeded anything that the observed outgassing could reasonably produce. The reaction forces from carbon dioxide and water vapor emission could account for only about 30% of the measured orbital deviations. The remaining acceleration required additional sources of momentum transfer. The direction of non-gravitational forces provided additional puzzles. In typical comets, reaction forces point roughly opposite to the direction of gas emission, creating predictable orbital perturbations. But 3I Atlas showed acceleration components that seemed disconnected from observed jet orientations, suggesting either undetected gas emission or alternative force mechanisms. Analysis of the Mars encounter provided crucial constraints on possible force sources. The gravitational influence of Mars itself was precisely calculable and could be removed from trajectory measurements, isolating any additional effects. The data revealed that non-gravitational accelerations actually increased during the close planetary approach, reaching maximum values when the visitor was nearest to Mars. This correlation was deeply puzzling. Mars's weak magnetic field and thin atmosphere couldn't reasonably explain enhanced non-gravitational forces through electromagnetic or atmospheric interactions. Yet the timing suggested some form of coupling between 3I Atlas's dynamics and its proximity to the red planet. Solar radiation pressure offered another potential explanation for trajectory anomalies. Sunlight carries momentum that can push lightweight objects, particularly those with high reflectivity or large surface, to mass ratios, but calculations based on 3I Atlas's observed brightness and estimated size suggested radiation pressure effects, orders of magnitude smaller than the measured accelerations. The Yarkovsky effect, which causes small rotating objects to experience forces due to thermal radiation patterns, provided yet another theoretical mechanism. But this effect depends strongly on rotation rate and surface thermal properties, both of which remained poorly constrained for 3I Atlas, despite extensive observational campaigns. Perhaps most intriguingly, the trajectory analysis revealed evidence for what appeared to be course corrections during the solar system passage. Rather than showing the smooth, predictable evolution expected from natural forces, the orbital deviations showed discrete jumps at specific times that corresponded to periods of enhanced activity or brightness changes. The precision of these apparent course corrections strained explanations based on random outgassing events. Natural jet activity produces chaotic force variations that average out over time. The trajectory data suggested something more systematic: acceleration changes that seemed purposeful rather than accidental. Computer modeling of various force scenarios failed to produce satisfactory matches to the observed trajectory deviations. Even combining multiple mechanisms, outgassing, radiation pressure, Yarkovsky effects, and electromagnetic interactions, couldn't fully explain the complex pattern of accelerations detected throughout the encounter. The trajectory anomalies became more pronounced during the post-perihelion phase, as if the thermal stress of close solar approach had activated new mechanisms for momentum transfer. The accelerations showed no signs of declining despite decreasing solar input and reduced outgassing activity. Long-term projections based on the measured non-gravitational forces suggested that 3I Atlas would follow a slightly different interstellar trajectory than initially calculated. The course corrections, whatever their origin, had measurably altered the visitor's future path through the galaxy. The orbital analysis left astronomers with an uncomfortable conclusion. their most precisely tracked interstellar visitor, was being accelerated by forces that remained completely mysterious, despite months of intensive study. The chemical fingerprints embedded within 3I Atlas's spectroscopic signatures told a story of birth in an alien stellar environment, but decoding that story required unraveling billions of years of galactic evolution and stellar nucleosynthesis that had shaped the visitor's parent system long before our own sun began to shine. The isotopic ratios detected in the visitor's outgassing provided the most direct clues about its formation environment. The carbon-12 to carbon-13 ratio differed significantly from solar system values, suggesting origin around a star with different nuclear processing history. The enhanced heavy isotope abundances pointed towards stellar environments enriched in supernova ejecta regions, where massive star explosions had seeded the interstellar medium with elements forged in stellar cores. The oxygen isotope signatures revealed additional constraints on formation conditions. The ratios of oxygen 1:6, oxygen 1:7, and oxygen 18 inches 3. I Atlas's water vapor and carbon dioxide emissions suggested incorporation of materials from multiple stellar sources. This isotopic complexity implied formation in a region where various stellar populations had contributed to local chemical abundances over extended timescales. Sulfur chemistry provided insights into the thermal conditions during the visitor's original accretion. The detection of both hydrogen sulfide and sulfur dioxide required formation environments where sulfur-bearing compounds could exist in different oxidation states simultaneously. Such conditions typically occurred in specific temperature and pressure zones within protoplanetary disks, offering potential constraints on the orbital distance where 3I Atlas originally formed. The organic molecular inventory suggested chemical processing in warm molecular cloud environments or active star-forming regions. Complex hydrocarbons like those detected in the visitor's spectrum typically required ultraviolet irradiation of simpler precursor molecules, indicating formation in regions with active stellar energy sources, rather than cold, quiescent interstellar environments. The carbon dioxide dominance that characterized 3I Atlas throughout its solar system encounter provided additional clues about its birth environment. In typical protoplanetary disk models, carbon dioxide abundance peaks in intermediate temperature zones, regions warm enough to prevent methane formation, but cool enough for CO2 condensation. This chemical signature placed the visitor's formation zone at distances roughly equivalent to the asteroid belt in our solar system. But the specific carbon dioxide to water ratio observed in 3I Atlas required formation conditions unlike those in our local stellar neighborhood. Theoretical models suggested that such extreme volatile ratios could result from formation around lower mass stars with different thermal profiles, or in disks with unusual carbon and oxygen abundances inherited from previous stellar generations. The noble gas isotope ratios detected during post-perihelion observations offered the most tantalizing clues about stellar environment specifics. Argon and xenon isotopic signatures could potentially identify not just the general type of star system where 3I Atlas formed, but possibly even the specific stellar population or galactic location of its origin. The heavy element abundances inferred from spectroscopic analysis suggested formation in a region with metallicity higher than our local galactic environment. This enhanced heavy element content pointed toward formation in the galaxy's thick disk population stars that formed during earlier epochs when supernova rates were higher and chemical enrichment proceeded more rapidly. Temporal constraints from galactic dynamics suggested that 3I Atlas might have been wandering interstellar space for 4 to 8 billion years. Based on its current galactic velocity and trajectory, this implied formation during the galaxy's middle age, when stellar populations and chemical abundances differed substantially from current conditions. The preservation of complex chemistry across such extended timescales raised questions about radiation processing. During the interstellar journey, cosmic ray bombardment should have gradually altered surface and near-surface compositions. Yet 3I Atlas retained chemical signatures that seemed to reflect its original formation environment with remarkable fidelity. Comparative analysis with solar system formation models revealed fundamental differences in the chemical processes that shaped 3I Atlas versus objects born in our local stellar environment. The visitor appeared to sample formation conditions that were simultaneously more chemically complex and thermodynamically extreme than those that produced familiar solar system materials. The chemical diversity observed in just 3 interstellar visitors, 1I, Oumuamua, 2I divided by Borisov, and 3I Atlas, suggested that the galaxy contained formation environments spanning enormous ranges of temperature, pressure, chemical composition, and radiation fields. Each visitor sampled different stellar nursery conditions, creating a chemical library that reflected billions of years of galactic evolution. Understanding 3I Atlas's formation environment required reconstructing stellar conditions that existed long before Earth formed, in regions of space we might never directly observe. The visitor served as a chemical messenger from deep space and deep time, carrying information about cosmic processes that shaped matter across scales, from molecular to galactic. The very existence of 3I Atlas as a chemically active, structurally coherent object presented one of the most profound puzzles in modern astronomy. How does cosmic debris survive millions or billions of years wandering the hostile environment of interstellar space, while retaining the capacity for dramatic activity when it encounters a new stellar system? The challenges facing interstellar wanderers are almost inconceivably severe. Cosmic radiation continuously bombards objects traveling between stars, gradually breaking apart molecular bonds and rearranging chemical structures through radiolysis. High-energy particles from galactic sources carry enough energy to shatter atomic nuclei, creating cascades of secondary radiation that penetrate deep into solid materials. The radiation environment in interstellar space delivers doses that would sterilize any earthly organism within hours. Over millions of years, this bombardment should gradually erode surface materials, alter chemical compositions, and homogenize initially diverse structures into uniform processed layers. Yet 3I Atlas retained complex surface features and diverse chemistry that seemed inconsistent with extensive radiation processing. Micrometeorite bombardment presented another survival challenge. Interstellar space contains dust particles and debris that impact wandering objects at extremely high velocities. Even microscopic grains carry tremendous kinetic energy when striking at speeds of tens of kilometers per second. Over geological timescales, this sandblasting should erode surfaces and gradually fragment structural integrity. Temperature cycling added thermal stress to the survival equation. Objects traveling between star systems experience extreme temperature variations as they pass through different radiation environments. The thermal expansion and contraction associated with these cycles should gradually crack and fragment materials, particularly the ice-rich compositions inferred for most interstellar visitors. Tidal forces from stellar encounters during the galactic journey created additional stress sources. When 3I Atlas passed near other star systems during its wandering, gravitational fields should have deformed its structure and potentially induced rotational changes or internal fracturing. Multiple stellar encounters over millions of years should have accumulated significant structural damage. Yet somehow, 3I Atlas had survived all these hazards while preserving both structural integrity and chemical activity. The preservation mechanisms remained largely mysterious, though several theoretical possibilities offered partial explanations for extended survival. Self-shielding provided one potential protection mechanism. If radiation processing created protective surface layers that absorbed high-energy particles before they could penetrate to deeper materials, internal composition might remain relatively pristine, despite surface alteration. Laboratory studies of radiation effects on ice and organic materials showed evidence for such protective crust formation. Internal thermal regulation could theoretically help preserve chemical complexity across extended timescales. If 3I Atlas possessed internal heat sources or exceptionally effective insulation, temperature variations might be minimized throughout its interior structure. Stable thermal environments would reduce chemical decomposition rates and preserve volatile inventories that would otherwise be lost. The chemical preservatives detected in 3I Atlas's spectrum included molecular species known for their stability under radiation exposure. Complex organic compounds could potentially serve as natural protective agents, absorbing radiation energy and preventing damage to more fragile materials. This chemical armor might explain the preservation of both structural features and volatile reservoirs. Size-dependent survival effects could contribute to preservation across interstellar journeys. Larger objects possess greater thermal mass and shorter surface-to-volume ratios, potentially providing better protection for interior materials. The several-kilometer scale of 3I Atlas placed it in a size regime where survival mechanisms might operate more effectively than for smaller debris. Rotational dynamics offered another preservation mechanism. Tumbling objects present different surface regions to radiation sources over time, distributing damage rather than concentrating it on specific areas. The stable rotation observed in 3I Atlas might actually represent optimal configuration for survival, though this contradicted observations of rotational stability. The formation environment might have endowed 3I Atlas with inherent durability that facilitated long-term survival. If the visitor formed under conditions that favored structural integrity and radiation resistance, it might possess natural advantages for surviving interstellar journeys that objects formed under different conditions would lack. Magnetic shielding provided a more speculative but intriguing preservation mechanism. If 3I Atlas somehow retained magnetic field generation, a capability, it could deflect charged particle radiation and reduce exposure to damaging cosmic rays. However, natural objects rarely possess strong magnetic fields, and maintaining such fields across geological timescales required energy sources that seemed implausible. The survival achievements of 3I Atlas challenged fundamental assumptions about material stability on cosmic timescales. The visitors' continued activity suggested that interstellar space, despite its apparent hostility, might actually provide environments where complex materials could be preserved across billions of years under the right conditions. Dr. Avi Loeb's analysis of 3I Atlas exemplified the delicate balance between scientific openness and rigorous skepticism that defines frontier research in astronomy. His detailed examination of the visitors' anomalous properties raised questions that the astronomical community found both compelling and deeply uncomfortable. Loeb's approach to the 3I Atlas mystery was methodically systematic, beginning with careful documentation of observed anomalies and progressing through increasingly exotic explanations only as natural mechanisms proved inadequate. His August analysis correctly predicted the detection of the visitor's subtle tail weeks before other researchers identified the feature, demonstrating the value of pushing observational data to detection limits. The size discrepancy formed a cornerstone of Loeb's analysis. His brightness-based estimates suggested a nucleus potentially tens of kilometers across, dramatically larger than Hubble's upper limit of 5.6 kilometers. This discrepancy implied either incorrect assumptions about surface reflectivity or optical properties unlike any known natural materials. Both possibilities challenged conventional interpretation of the visitor's nature. The energy balance calculations proved even more troubling. Loeb's detailed analysis of outgassing rates and thermal requirements revealed power demands that exceeded reasonable estimates of solar heating by factors of 10 to 20. The sustained activity levels required energy sources beyond simple thermal input, leading to speculation about internal power generation mechanisms. The trajectory optimization observations provided additional foundation for unconventional hypotheses. Loeb noted that 3I Atlas's path through the solar system displayed geometric properties that maximized observational opportunities from Earth. While such optimization could result from coincidence, the probability calculations suggested odds approaching 1 in several million for purely random occurrence. The technological hypothesis emerged from Loeb's systematic elimination of natural explanations, rather than from preference for exotic interpretations. When conventional mechanisms failed to account for observed properties, responsible scientific methodology demanded consideration of alternatives that might initially seem implausible, but remained consistent with physical laws. Loeb's analysis of possible artificial origins focused on testable predictions rather than speculative assertions. If 3I Atlas represented some form of technology, it should display characteristics distinguishable from natural phenomena through careful observation. The challenge lay in developing observational tests with sufficient sensitivity to detect artificial signatures if they existed. The Intercept mission proposals co-authored by Loeb represented perhaps the most concrete contribution to 3I Atlas science. Working with spacecraft trajectory specialists, he outlined detailed scenarios for redirecting existing missions toward close encounters with the visitor. These proposals included specific technical requirements and scientific objectives that could potentially resolve questions about the object's nature. The peer review process surrounding Loeb's analysis demonstrated both the strengths and limitations of scientific consensus building. While his observational documentation received general acceptance, interpretations involving possible artificial origins faced substantial skepticism from colleagues who favored conventional explanations, despite their apparent inadequacy. The media response to Loeb's work illustrated the challenges of communicating preliminary scientific hypotheses to general audiences. Headlines about alien technology distorted carefully qualified speculation into sensationalized claims that misrepresented both the evidence and the scientific process of hypothesis evaluation. The broader scientific community's reaction reflected legitimate concerns about the extraordinary evidence standards required for extraordinary claims. While acknowledging the validity of observed anomalies, most researchers preferred to await additional data rather than embracing explanations that challenged fundamental assumptions about interstellar objects. Loeb's collaboration with mainstream observational teams demonstrated his commitment to evidence-based inquiry rather than advocacy for particular interpretations. His involvement in data analysis and theoretical modeling contributed to scientific understanding, regardless of whether his more speculative hypotheses proved correct. The temporal constraints surrounding 3I Atlas observations added urgency to theoretical debates about the visitor's nature. With the object rapidly fading as it departed the solar system, opportunities for gathering decisive evidence were disappearing. The window for definitive hypothesis testing was measured in months rather than years. The methodological questions raised by the 3I Atlas controversy extended beyond astronomy to fundamental issues about scientific epistemology. How should researchers balance healthy skepticism against premature dismissal of genuinely anomalous data? What evidentiary standards should apply to phenomena that challenge existing theoretical frameworks? The long-term implications of the RUB 3I Atlas debate would likely influence how future anomalous observations are evaluated and discussed. The controversy established important precedents for balancing scientific rigor with intellectual openness when confronted with data that didn't fit conventional expectations. Whether Loeb's technological hypotheses ultimately proved correct or incorrect, his systematic documentation of anomalies and willingness to consider unconventional explanations contributed essential perspectives to humanity's first detailed study of an active interstellar visitor. As 3I Atlas faded into the depths of space during early 2026, the most comprehensive study of an interstellar visitor in history concluded with a sobering realization. The fundamental questions that had motivated the entire observational campaign remained largely unanswered, replaced by new mysteries that challenged every assumption about cosmic debris and the space between stars. The nuclear composition remained frustratingly elusive. Despite months of intensive spectroscopic analysis, while observations had catalogued dozens of molecular species in the visitor's outgassing, the bulk composition of the solid nucleus itself remained largely unknown. Was 3I Atlas primarily water ice with trace contaminants? Or did it represent some exotic mixture of materials unknown in solar system objects? The answer would determine whether the visitor represented an extreme example of familiar physics or something genuinely unprecedented. The internal structure questions proved equally persistent. The extended coma observations suggested either a highly porous nucleus with enormous internal surface area or distributed reservoirs of volatile materials spread throughout a complex interior architecture. Yet no theoretical model successfully reconciled the structural requirements with the observed thermal and chemical behavior. The visitor's interior remained as mysterious as when first discovered. The energy source puzzle had only deepened throughout the encounter. Despite exhaustive analysis of thermal budgets and outgassing rates, no combination of solar heating and reasonable internal processes could explain the sustained activity levels. Either 3I Atlas possessed energy storage or generation mechanisms beyond current understanding, or fundamental assumptions about interstellar object behavior were completely incorrect. The rotation anomalies resisted explanation despite detailed photometric monitoring and multiple viewing angle observations. The visitor's unusual rotational stability challenged basic principles of small body dynamics, yet no proposed mechanism successfully accounted for the observed behavior. The spin state remained as puzzling as any other aspect of 3I Atlas's behavior. The chemical evolution observed throughout the encounter raised questions about preservation mechanisms that had operated across millions of years in interstellar space. How had complex organic molecules survived cosmic ray bombardment and extreme temperature variations? What processes had maintained chemical activity potential across geological timescales? The preservation mechanisms remained completely theoretical. The formation environment constraints remained frustratingly broad, despite detailed isotopic and chemical analysis. While observations suggested origin in the galaxy's thick disk population around 4 to 8 billion years ago, pinpointing specific stellar types or formation conditions required precision beyond current analytical capabilities. The visitor's birthplace remained lost in cosmic history. The trajectory anomalies had been documented with high precision, but their physical origins remained mysterious. The non-gravitational accelerations exceeded anything explicable through conventional outgassing. Yet no alternative mechanism provided satisfactory explanation. Whether the forces resulted from natural processes or something more exotic remained an open question. The survival mechanisms that had preserved 3I Atlas's activity potential across interstellar distances remained largely speculative. While various protective processes had been proposed, none fully explained how such a complex, volatile, rich object could maintain structural and chemical integrity across cosmic timescales. The preservation puzzle remained unsolved. The relationship between the visitor's anomalous properties, unusual chemistry, excessive energy output, rotational stability, and trajectory deviations remained unclear. Were these independent characteristics that happened to occur in the same object, or did they represent different manifestations of underlying properties that fundamentally distinguished 3I Atlas from conventional solar system materials? The statistical significance of 3I Atlas's unusual characteristics raised broader questions about the interstellar object population. Did the visitor represent a rare extreme within an otherwise normal distribution, or did it exemplify properties that might be common among interstellar debris but had simply never been observed with sufficient detail? The answer would determine whether 3I Atlas was an anomaly or a revelation. The observational limitations had become painfully apparent throughout the encounter. Despite deploying humanity's most sophisticated instruments, crucial measurements remained beyond current technological capabilities. Direct surface composition analysis, internal structure determination, and energy source identification required observational techniques that didn't exist. The visitor had exposed the limits of remote sensing technology. The theoretical framework inadequacies had become equally apparent. Existing models of interstellar object behavior, developed primarily from solar system analogies, proved insufficient for explaining 3I Atlas's characteristics. New theoretical approaches would be needed to accommodate objects that challenged fundamental assumptions about cosmic debris. Perhaps most frustratingly, the time constraints had prevented definitive resolution of any major questions. The visitor's rapid departure meant that many crucial observations remained impossible to conduct. Future interstellar visitors might display completely different characteristics, making the 3I Atlas data irreplaceable despite its incompleteness. The legacy of unanswered questions would influence interstellar visitor research for decades to come. 3I Atlas had demonstrated that cosmic debris could possess properties far exceeding theoretical expectations. but it had also shown that understanding such objects would require capabilities beyond current scientific infrastructure. The universe had delivered another reminder that human knowledge remained incomplete. The 3I Atlas encounter had transformed interstellar visitor science from curiosity-driven research into urgent infrastructure development, as astronomers worldwide recognized that the next cosmic messenger might arrive with even less warning and display characteristics that challenged human understanding even more dramatically than this ancient wanderer from the deep. The Vera Rubin Observatory represented humanity's most ambitious attempt to systematically catalogue the interstellar debris population. Beginning full operations in 2025, its 8.4-meter mirror and 3.2 gigapixel camera would map the entire southern sky every 3 nights, achieving sensitivity levels that dwarfed previous survey capabilities. Theoretical estimates suggested Rubin might detect anywhere from 1 to 70 interstellar visitors per year, transforming rare cosmic accidents into routine scientific opportunities. The statistical revolution promised by Rubin would fundamentally change how researchers approached interstellar object science. Instead of treating each visitor as a unique mystery, astronomers would identify population trends, chemical correlations, and behavioral patterns that revealed underlying physics of planetary system formation and evolution across the galaxy. 3I Atlas would serve as a crucial calibration point for this statistical approach. The European Space Agency's Comet Interceptor mission embodied a new philosophy of preparedness for cosmic opportunities. Scheduled for launch in 2029, this innovative spacecraft would position itself at gravitationally stable Lagrange point L2, roughly 1.5 million kilometers from Earth, where it would wait in readiness for targets of opportunity. When the next interstellar visitor arrived, Comet Interceptor could redirect toward intercept trajectories within months rather than years. The mission design philosophy recognized the fundamental challenge posed by fast-moving interstellar visitors. We needed to be ready before they arrived, not scrambling to respond after discovery. The spacecraft would carry instruments specifically designed for high-speed encounters with pristine objects, including cameras capable of resolving surface features, spectrometers for compositional analysis during brief flybys, and dust collectors for capturing actual material samples. The rapid response frameworks developed during the 3I Atlas encounter established new protocols for coordinating global observational resources. When cosmic messengers appeared, traditional astronomical culture, which relied on carefully planned, peer-reviewed observing programs, had proven too slow for studying rapidly evolving interstellar visitors. Instead, target of opportunity protocols could redirect major facilities within days of discovery. The data pipeline innovations created during 3I Atlas observations set new standards for real-time integration of multi-observatory campaigns. The seamless combination of data from Hubble, Webb, SPA-TEREX, and ground-based facilities had created unprecedented synergies where each instrument's capabilities complemented the others. This collaborative framework provided templates for studying future visitors with even greater efficiency. The theoretical framework expansions, forced by 3I Atlas's anomalous behavior, established new paradigms for understanding interstellar objects. The visitor had demonstrated that cosmic debris could possess properties far exceeding conventional expectations, requiring theoretical models that accommodated exotic chemistry, unusual dynamics, and energy sources beyond simple thermal processes. The technological development, driven by interstellar visitor requirements, had accelerated innovations in several critical areas. Improved spectrometer sensitivity, faster image processing algorithms, more sophisticated orbital mechanics software, and enhanced target tracking systems all benefited from the demanding requirements of studying faint, fast-moving objects with complex behavior. The international cooperation, catalyzed by 3I Atlas, provided models for addressing scientific challenges that transcended national boundaries. When the universe delivered phenomena requiring rapid, coordinated responses, the astronomical community had demonstrated remarkable ability to set aside territorial concerns and focus on shared scientific objectives. This collaborative spirit would prove essential for future encounters. The public engagement strategies, refined during the 3I Atlas campaign, established important precedents for communicating about genuinely anomalous observations. The challenge of maintaining scientific honesty while avoiding sensationalized misinterpretation had required careful balance between acknowledging genuine mysteries and preventing unfounded speculation about exotic explanations. The industrial partnerships forged during the 3I Atlas observational campaign created new models for leveraging commercial space capabilities for scientific objectives. Private sector involvement in tracking, data analysis, and even spacecraft missions offered pathways for expanding scientific capabilities beyond traditional government-funded programs. The educational impact of interstellar visitor discoveries was already reshaping curricula in astronomy and planetary science programs. Students learning about planetary formation now studied examples from other star systems, not just local solar system objects. The chemical diversity revealed by 3I Atlas and its predecessors provided concrete evidence that planetary environments differed dramatically from Earth-centric examples. The next interstellar visitor would encounter a scientific community fundamentally transformed by the 3I Atlas experience. Survey capabilities, response protocols, observational techniques, and theoretical frameworks had all evolved to accommodate objects that challenged conventional expectations about cosmic debris. Yet the most important lesson from 3I Atlas might be the recognition that each interstellar visitor would likely present unique challenges that required adaptive, flexible approaches. Rather than standardized procedures, the universe seemed determined to keep sending messengers that refused to conform to human expectations about how cosmic debris should behave. Preparation for the next visitor required balancing readiness for known challenges with openness to completely unexpected phenomena that might redefine understanding of interstellar objects entirely. The brief catalogue of confirmed interstellar visitors: 1I, Oumuamua; 2I, divided by Borisov; and 3I Atlas, represented humanity's first systematic sampling of the vast population of cosmic debris that fills the space between stars, and the diversity revealed by just these three objects suggested that our galaxy harbored formation environments and evolutionary processes far more varied than any theoretical model had predicted. Statistical analysis of the detection rates implied a population density that staggered the imagination. If the discovery frequency achieved by current survey systems accurately reflected the true abundance of interstellar objects, then every cubic light-year of galactic space contained thousands of wandering fragments ejected from planetary systems throughout cosmic history. The number of interstellar objects within just our local stellar neighborhood might exceed the total population of solar system asteroids and comets combined. The chemical diversity revealed by 3 visitors challenged every assumption about planetary formation processes. 1I, Oumuamua, had shown no detectable outgassing, suggesting either complete volatile depletion or unusual composition. 2I, divided by Borisov, displayed carbon monoxide enhancement, characteristic of formation in extremely cold environments. 3I Atlas dominated with carbon dioxide chemistry that implied intermediate formation temperatures. Each visitor sampled different stellar nursery conditions. The morphological contrasts were equally striking. Oumuamua's extreme elongation pushed the boundaries of natural object shapes, leading to speculation about artificial origins. Borisov appeared conventionally spherical, with typical cometary features. 3I Atlas occupied middle ground, with complex surface activity, but unusual rotational stability. The shape diversity suggested formation processes spanning enormous ranges of gravitational, thermal, and collision environments. The size distribution inferred from 3 objects remained highly uncertain, but preliminary estimates suggested interstellar visitors might span size ranges from meters to hundreds of kilometers in diameter. The discovery bias toward larger, more active objects meant that the true population likely contained millions of smaller fragments for every detectable visitor, creating a hierarchy of debris that reflected the violent processes of planetary system evolution. The chemical inventory revealed by interstellar visitors expanded the known range of volatile compositions beyond anything observed in solar system objects. The carbon dioxide dominance of 3I, Atlas in particular, suggested formation environments where thermodynamic conditions favored carbon-bearing compounds over the hydrogen-oxygen chemistry that dominated our local planetary materials. Such environments might be common around certain types of stars or during specific epochs of galactic evolution. The survival mechanisms that allowed complex objects like 3I Atlas to maintain chemical activity across millions of years in interstellar space remained largely mysterious, but their existence implied that preservation processes operated more effectively than previously assumed. The galaxy might contain vast archives of ancient materials, preserved in cosmic cold storage, carrying information about stellar environments that existed billions of years ago. The ejection mechanisms that launched objects like 3I Atlas into interstellar space required violent gravitational encounters with giant planets, or close stellar approaches that fundamentally reshaped entire planetary systems. The detection of even a few such visitors implied that planetary system disruption events occurred far more frequently than previously assumed, suggesting a galaxy where planetary architectures remained dynamically unstable across cosmic timescales. The galactic context of interstellar debris revealed connections between stellar evolution, chemical enrichment, and planetary formation that operated on scales spanning the entire galaxy. Objects like 3I Atlas served as chemical messengers that mixed materials between star systems, potentially playing roles in galactic chemical evolution that had never been recognized. The temporal distribution of interstellar objects implied continuous production across galactic history. The apparent ages of detected visitors suggested that planetary systems had been ejecting debris for billions of years, creating accumulating populations that grew with each stellar generation. The oldest visitors might carry chemical signatures from the galaxy's youth, when stellar populations and formation conditions differed dramatically from current environments. The velocity distributions of interstellar visitors revealed information about galactic dynamics and stellar populations that complemented traditional astronomical observations. The high velocities characteristic of objects like 3I Atlas suggested origins in stellar populations with different kinematic properties than our local neighborhood, providing samples from galactic regions that might otherwise remain observationally inaccessible. The discovery methods that had revealed 3I Atlas and its predecessors were strongly biased towards specific size ranges, activity levels, and trajectory geometries. The true interstellar population likely contained vast numbers of objects that remained invisible to current detection techniques, including dormant fragments, smaller debris, and visitors approaching from directions that minimized observational opportunities. The future survey capabilities, promised by facilities like the Vera Rubin Observatory, would transform population studies from anecdotal case studies into rigorous statistical science. With hundreds of interstellar visitors expected over the coming decades, researchers would finally possess sample sizes large enough to reveal population trends, chemical correlations, and formation-environment relationships. The broader implications of interstellar visitor diversity suggested that planetary formation processes operated under conditions spanning enormous ranges of stellar mass, chemical abundance, radiation environment, and dynamical architecture. The galaxy represented a vast laboratory where nature had experimented with countless approaches to building planetary systems, each one producing characteristic debris signatures that eventually wandered into our observational sphere. The arrival of 3I Atlas had transformed humanity's understanding of our place in the universe, from isolated observers in a vast emptiness to participants in a dynamic galactic community, where materials, chemistry, and possibly even life itself moved freely between star systems across cosmic timescales that dwarfed human civilization. The recognition that interstellar space contained vast populations of wandering objects fundamentally altered the cosmic perspective that had defined human thought since we first looked up at the stars. Rather than existing in splendid isolation within our solar system, we inhabited a galaxy where debris regularly crossed the boundaries between stellar neighborhoods, creating slow but steady exchange of materials that connected distant worlds across light-years of space. The chemical diversity revealed by interstellar visitors suggested that the galaxy harbored formation environments spanning enormous ranges of temperature, pressure, radiation intensity, and elemental abundance. Each star system served as a laboratory where unique combinations of physical conditions produced characteristic chemical signatures that eventually dispersed into interstellar space through planetary system evolution and disruption. The temporal scales involved in interstellar debris transport implied that materials currently arriving at our solar system might have begun their journeys when the galaxy was younger. Stellar populations were different, and chemical abundances reflected earlier stages of cosmic evolution. Visitors like 3I Atlas served as time capsules that carried information about galactic conditions billions of years in the past. The preservation of complex chemistry across interstellar journeys suggested that the space between stars, despite its apparent hostility, actually provided environments where organic molecules and volatile compounds could survive across geological timescales. This cosmic preservation system might play crucial roles in distributing the chemical building blocks of life throughout the galaxy. The panspermia hypothesis gained new relevance in light of interstellar visitor discoveries. If objects like 3I Atlas could maintain chemical complexity during million-year journeys between star systems, they might also transport biological materials or organic precursors that could seed new worlds with life's chemical foundations. The galaxy might represent an interconnected biological system, where life's building blocks moved freely between suitable environments. The formation environment diversity, implied by different interstellar visitors, suggested that the galaxy contained countless experiments in planetary system architecture. Some stellar systems produced debris rich in carbon dioxide, like 3I Atlas. Others generated carbon monoxide-enhanced materials, like 2I divided by Borisov. Still others might create chemical combinations never seen in our local environment. The survival and activity capabilities demonstrated by 3I Atlas challenged assumptions about the habitability requirements for life itself. If complex chemistry could persist across interstellar distances and remain active after millions of years in space, life might prove more resilient and widely distributed than previously assumed. The boundaries of habitability might extend far beyond traditional planetary environments. The energy source mysteries associated with 3I Atlas raised questions about natural processes that might operate throughout the galaxy but remain unrecognized due to observational limitations. If interstellar objects could maintain activity through mechanisms beyond conventional thermal processes, similar phenomena might occur in other cosmic environments where they had never been detected or studied. The trajectory anomalies and rotational stability exhibited by 3I Atlas suggested that natural objects might possess self-regulation capabilities that exceeded theoretical predictions. Such properties might represent common features of cosmic debris that had simply never been observed with sufficient precision to reveal their existence. The statistical implications of interstellar visitor discoveries transformed estimates of material exchange rates between star systems from theoretical speculation into observable phenomena with measurable frequencies. The galaxy operated as a vast mixing system where planetary materials moved continuously between stellar environments, homogenizing chemical compositions and potentially facilitating biological exchange on cosmic scales. The technological implications of objects like 3I Atlas raised possibilities about natural phenomena that might appear artificial to observers with limited understanding of cosmic processes. The boundary between natural and artificial became increasingly difficult to define when dealing with objects whose properties exceeded conventional theoretical expectations. The observational limitations revealed by 3I Atlas studies demonstrated that current scientific capabilities barely scratched the surface of understanding cosmic phenomena that operated on scales and timescales beyond terrestrial. experience. Each interstellar visitor exposed new gaps in theoretical knowledge and observational technique. The educational transformation prompted by interstellar visitor discoveries was reshaping how humans understood their cosmic context. Students learning about planetary science now studied examples from throughout the galaxy, rather than just local solar system objects. The universe had become a more intimate, connected place, where distant worlds contributed directly to our scientific understanding. The philosophical implications of interstellar visitor diversity challenged anthropocentric assumptions about the uniqueness or centrality of Earth's chemical and biological environment. The galaxy contained formation conditions that produced materials unknown in our local system, suggesting that life might arise under circumstances completely different from terrestrial conditions. The future exploration possibilities opened by interstellar visitor studies offered pathways for learning about stellar environments that human spacecraft might never reach directly. Each visitor represented a free sample delivery from alien worlds, providing information about cosmic processes that operated across distances and timescales beyond practical exploration limits. The cosmic context, revealed by 3I Atlas and its predecessors, suggested that humanity existed within a universe far more dynamic, interconnected, and chemically diverse than previous generations had imagined. A universe where the space between stars teemed with messengers carrying news from countless other worlds. As 3I Atlas disappeared into the cosmic deep in late 2026, fading beyond the detection limits of even humanity's most powerful telescopes, the ancient visitor left behind more than scientific data and theoretical puzzles. It had fundamentally transformed our expectations about the universe and our readiness to receive its next messenger from the space between stars. The visitor's current trajectory would carry it through the outer reaches of our solar system for several more years, before it finally escaped the sun's gravitational influence entirely. By 2030, 3I Atlas would join the vast population of interstellar wanderers, resuming a journey that might continue for millions more years before encountering another star system. Yet its brief passage through our neighborhood had revealed that the cosmos contained phenomena far stranger and more wonderful than any theoretical framework had predicted. The lessons learned from 3I Atlas would influence interstellar visitor research for decades to come. The observational techniques refined during its study, the theoretical frameworks expanded to accommodate its anomalous properties, and the international cooperation protocols developed for rapid response would all prove invaluable when the next cosmic messenger arrived. And statistical projections suggested that arrival was not a matter of if, but when. The Vera Rubin Observatory's systematic sky surveys were already detecting candidate objects that might represent the fourth, fifth, and sixth confirmed interstellar visitors. Each new discovery would add crucial data points to humanity's growing census of galactic debris, potentially revealing whether 3I Atlas represented a rare anomaly or a typical example of objects that had previously escaped detailed study. The technological developments driven by 3I Atlas research continued advancing capabilities for studying fast-moving, faint targets with complex behavior patterns. Improvements in spectrometer sensitivity, automated tracking systems, and real-time data integration would provide future visitors with observational coverage that exceeded anything possible during 3I Atlas's encounter. The theoretical frameworks expanded to accommodate the visitor's unusual properties would require further testing through observations of additional interstellar objects. Were the energy source mysteries, rotational anomalies, and chemical complexities unique to 3I Atlas? Or did they represent common characteristics of interstellar debris that had never been recognized? Only larger sample sizes would provide definitive answers. The public engagement strategies refined during the 3I Atlas campaign had demonstrated both the opportunities and challenges associated with communicating about genuinely anomalous scientific observations. The experience provided valuable lessons for maintaining accuracy while acknowledging uncertainty when discussing phenomena that challenged established understanding. The next interstellar visitor might arrive with completely different characteristics that required entirely new observational approaches. Perhaps it would be larger or smaller than previous examples, display different chemical signatures, or exhibit behaviors that made 3I Atlas seem conventional by comparison. The universe had already demonstrated its capacity for delivering cosmic surprises that exceeded human imagination. The ESA Comet Interceptor mission, waiting patiently at Lagrange point L2, represented humanity's most ambitious preparation for the next encounter. When the fourth interstellar visitor appeared, this spacecraft could potentially achieve the close-range observations that had remained impossible for 3I Atlas. Direct measurements might finally resolve questions about internal structure, composition, and energy sources that had puzzled researchers throughout the 3I Atlas encounter. The statistical predictions based on current detection rates suggested the next confirmed interstellar visitor might arrive within 2 to 5 years. But the universe operated according to its own schedule, not human expectations. The next messenger might appear tomorrow or decades hence, carrying its own unique combination of mysteries and revelations about cosmic processes that operated far beyond our solar system boundaries. The broader implications of interstellar visitor research extended beyond pure scientific curiosity to fundamental questions about life, intelligence, and cosmic evolution. If the galaxy contained such diverse formation environments and preservation mechanisms, what might this suggest about the distribution of life itself? Could biological materials survive interstellar journeys as successfully as the complex chemistry observed in 3I Atlas? The philosophical transformation, prompted by 3I Atlas, would continue influencing human perspectives about our place in the universe. We no longer observed the cosmos from isolation, but recognized ourselves as participants in galactic processes that connected star systems across vast distances and timescales. The universe had become a more intimate place, where distant events directly influenced our scientific understanding and cosmic perspective. As we await the next interstellar messenger, the questions raised by 3I Atlas remain largely unanswered. Was it a representative example of cosmic debris, or an extraordinary anomaly? Did its unusual properties reflect natural processes we had never previously encountered, or something that challenged basic assumptions about what was possible in the universe? The answers would come from continued observation, analysis, and theoretical development driven by encounters with additional visitors from the deep. Each new arrival would add pieces to the cosmic puzzle, gradually revealing the true nature of interstellar space and the objects that wander between stars. Somewhere in the darkness beyond our solar system, the next messenger is already traveling toward us, carrying its own secrets from alien worlds and distant times. When it arrives, we will be ready equipped with knowledge gained from 3I Atlas, prepared with improved instruments and techniques, and guided by the recognition that the universe continues to hold surprises that exceed our capacity for prediction. The cosmic conversation continues, and humanity is finally learning to listen.